Always got to test this microphone. One time I recorded an entire lecture with the microphone turned off.
No. You meant to do that.
Yeah. But that was back before YouTube, so it didn't matter anyways. It's lost now. Okay, so Peyton had a great question about molecular orbital theory. And we're looking at the MO diagrams for benzene. So if you've got the worksheet from Monday, which I did not put up. If you've got the worksheet from Monday, then you've got the molecular orbitals of benzene. Tuesday, I had a lot of brain fog, so it was really hard for me to communicate what was in my head, harder than it normally is. So I want to reiterate that the molecular orbital diagram of benzene is harder to predict than most other molecular orbitals. And rather than walking you through why its molecular orbital proves that it contributes this electronic stabilization, instead I'm going to show you how molecular orbital theory proves an electronic destabilization with something that we'll call anti-aromatic. But for right now, I want to remind you guys about the Frost circle, where we said take any cyclic structure, put it on a vertex, and now at every vertex, you draw a line that represents a molecular orbital. On the diagram that I've given you, I plugged it in, but you still can't see it. Well, it wouldn't matter. It wasn't pulled up anyways. On the diagram that I've given you, I have actually shown them as separate orbitals around each atom. This is just for clarity's sake, and I guess quite honestly because I don't have the capacity to actually hybridize those orbitals and show them to you as they would really look. So if I were to resketch this, that lowest most orbital, where it looks like every atom has a p orbital and they're all in phase, well, that p orbital actually starts to take on a shape like this. Clearer? Maybe. Here's a fun trick. If you can get those electrons, those two electrons that exist around the entire sphere, the entire ring at once, if you can get them to move in a circle, then you can generate a magnetic field, because electrons that move in a circle create a magnetic field perpendicular to that motion. Physics 2 type stuff. This is one of the reasons why NMR shows aryl hydrogens so far downfield to the left. It's not because those hydrogens are de-shielded and exposed to the magnet of NMR by an electronegative atom. It's just carbons. They're actually, the hydrogens attached to the ring are de-shielded because of this magnetic field that is induced by the cyclic moving of the aromatic electrons. It's very strange, but if you looked at an aromatic ring, you might not expect that two of the electrons can just spin around in a circle around the ring. But MO theory says that can happen. Lowest energy, one orbital, no nodes. At our second level, we'll see that there is one node, but these can go in different directions. If I take one node and I cut across two bonds, then I'll get these two sets of 3 atoms. But if I take a node and I cut through 2 atoms, I'll get 2 sets of 2 atoms. So again, I'm not actually showing the fact that these form bigger pi-looking orbitals. So on the left, I've got 3 atoms in phase, 3 atoms in phase, which more realistically would look a little bit like this. But it's much harder to communicate than what that image shows. And then again, similarly, this is just one big p orbital on top and one out of phase big p orbital on bottom. See, over here I actually drew them as in phase, and I didn't show them as out of phase. Why are these the same energy? Your question was, this has 4 orbitals, this has 6. Actually, no, this has 2 orbitals. It does consist of fewer atoms. This orbital only is located on top of 4 atoms. This also consists of 2 orbitals, out of phase with each other, but this orbital sits across all 6 atoms, which is a good observation. There's not much to learn about it, other than saying that 2 electrons behave across 2 sets of 3 atoms, and 2 electrons behave across 2 sets of 2 atoms.
So is that like the pi bond?
It's like the pi bond, but these are all the pi bonds. Because remember, this is benzene, and we said that there are 3 pi bonds. But it's not 3 sets of 2 atoms bonded. That's what valence bond theory, that's what bond line would have you predict. The 3 pi bonds are actually one pi bond where every atom is bonded together. All of them have a double bond. And then a pi bond where 3 are bonded and the other 3 are bonded, but there's a node between them. And then another pi bond where 2 are bonded and 2 are bonded with a node between them. We're not going to do it, but we could look at these orbitals as frontier orbitals to explain certain reactivity of the compound. For instance, if these electrons, which are the highest occupied molecular orbital, HOMO electrons, if these electrons were to act as a nucleophile, then I might be able to predict that it would look something like a pi bond reacting, because this orbital looks a bit like a regular, what we expect to think of as a pi bond. Ultimately, though, one node, 2 out of phase portions of the orbital, which is why these 2 types of orbitals are degenerate. They have the same energy, but they do take up space differently, and the electrons behave uniquely in them. As you move up another level, well, this time you actually keep all 4 atoms, but they all 4 become out of phase with each other. And on the left, you take these 2 groups of 3, you break them into 2 groups of 2 and 2 groups of 1. That's just going to take a little bit longer to draw out. But it looks a lot like this with those returned orbitals over those other spots. Does it look weird? Yes. Is that okay? Yes. It tells us that electrons do weird stuff. It's not as clean cut as just drawing a 6-membered ring with 3 extra lines in it. There's weird behavior that it has. For comparison, if we were drawing the pi molecular orbital for hexatriene, 6-carbon chain with 3 conjugated pi bonds, we would also get 6 molecular orbitals, but the molecular orbitals would be 3 that are lower in energy, 3 that are higher in energy, and they'd all be stacked. So our typical MO diagram takes this linear combination and creates linear orientation of energies. But the Frost circle takes this cyclic structure and points out that they have a different distribution of energies for those 6 molecular orbitals. This gets me to Huckel's rules, which is where I said we were going to leave off last class. this electronic stabilization, this stabilizing force that Huckel named as aromaticity. By the way, aromatics, the things that you can smell, came before aromatics, the electronically stable compounds. So not all fragrant molecules have aromatic rings, and not all compounds with aromatic rings are fragrant molecules. So aromatic is applied in two completely different senses. No pun intended. Huckel determined that you first need to have a cyclic structure. Remember that cyclic structure is what we noted in this first lowest energy MO, where two electrons basically just exist as a torus around the entire molecule. The second component is that it must be fully conjugated. What does it mean here to be fully conjugated? They all have the same hybridization? Not quite, because they could all be sp3 hybridized, in which case they would not be conjugated. Instead, they need to all have some sort of pi capacity in order to conjugate. So all sp or sp2 hybridized, and honestly, we see sp2 hybridized the most, but sp atoms can definitely be included in aromatic conjugated systems. The third point here is that it must be planar. And in my opinion, this planar rule is a bit outdated, because without being planar, the system can't be fully conjugated. So I want to give you an example of a system that isn't planar. We start by drawing an octagon. Oh, I should have done this in red. And then we add 4 bonds, or 4 pi bonds to make cyclooctatetraene. Of course, this looks flat because we've drawn it flat. But in reality, this molecule twists out of shape into a bowl. Can you see the bowl shape to it? This bowl means that the p orbitals on adjacent pi bonds can't actually overlap side to side to create the conjugation that we need. So if I sketch in the p orbitals for this pi bond, and then I sketch over the p orbitals for this pi bond, we see that the p orbitals meet at almost a 90-degree angle. And this idea of being conjugated is to have the side-to-side overlap of p orbitals, not a head-on overlap of p orbitals. So a structure that is not planar is also not conjugated. So by nature of needing a planar molecule, we're really just saying to ensure that every atom is planar. All right, so these were the original rules. The structure is cyclic, the structure is fully conjugated, the structure is planar. And then a new rule was added on afterwards because there were certain compounds that fit these requirements, and instead of being as energetically stable as predicted, or being more energetically stable than predicted, some compounds ended up being less energetically stable. So there is an energetic stabilization that comes from these 3 features, and an energetic destabilization that comes from these 3 features. So if it follows these rules, then we call it aromatic if the number of pi electrons is equal to some solution, just any way to solve it, with a whole number of 4n plus 2. N is physically irrelevant. It is not a constant, it's not a value, it's not a relationship. It is just a means to an end, not an n. For example, if n equals 0, then 4 times 0 plus 2 means that 2 pi electrons is an aromatic system. If n equals 1, then 6 pi electrons is a solution to an aromatic system. What has 6 pi electrons? Famously aromatic? Benzene, the aromatic ring. And then it goes on. N equals 2 means 10 pi electrons is an aromatic system, and so on. But we label a compound as anti-aromatic if the number of pi electrons is equal to 4n. So now we see a new set of pi electron values that create this destabilizing electronic force. If my system has 4 pi electrons, it's anti-aromatic. If my pi system has 8 pi electrons, it's anti-aromatic. And again, this is against expected computational values. We found that systems were either more stabilized or destabilized. Yes? Oh, because that doesn't make any sense. Sorry. Sorry, it shouldn't be n equals 0. It should be n equals 1 and n equals 2. Thank you, Yoon. Okay, so I want to take you guys through some examples. First, let's consider the molecule 1,4-cyclohexadiene. Cyclohexadiene. Is this compound aromatic, anti-aromatic, or non-aromatic? Cyclohexadiene. Aromatic, anti-aromatic, or non-aromatic? Why? Is it cyclic? Is it fully conjugated? No? Fully conjugated means every atom is sp or sp2 hybridized. It has sp3 atoms in the structure. Right here, sp3, non-aromatic. Okay, what about the compound cyclopentadienyl anion, which can be formed by taking a good base and deprotonating cyclopentadiene. Cyclopentadiene gets deprotonated, it forms the cyclopentadienyl anion. I love that word, by the way. Cyclopentadienyl anion. Aromatic or aromatic, anti-aromatic, or non-aromatic. Is it cyclic? Is it cyclic? Yes. Is it fully conjugated? Okay, well, we know that every carbon in the alkenes is sp2. So the one we're really interested in is the one on top, right? Our rules for hybridization so far have been count the electron regions and then count up to that hybridization, right? How many electron regions are on that carbon? 2 carbon-carbon bonds, 1 bond to hydrogen, and the lone pair. So 4 electron regions, we would reason that this carbon at the top is sp3 hybridized. If that were true, it would break rule number 2. This would be a non-aromatic. But let me ask you this. Why does an atom take on sp3 hybridization in the first place? What benefit does the atom get from putting electrons in an sp3 hybridized orbital rather than into just an atomic orbital in the first place? Why does it hybridize its orbitals?
More neighbors for stability.
More neighbors, better stability. Ella, what did you want to add to that?
I just said stability.
Stability? So it gets stability out of hybridization. What is it stabilizing? Its charges? Its electrons are becoming more stable. Because if you want to put 4 groups around the atomic orbitals, everything will be at 90-degree angles or less. And that's a lot of electron repulsion. So by hybridizing the orbitals, you get bigger bond angles, less electron repulsion. So the entire point of hybridizing to sp3 using our little tricks is for energetic stabilization. Do you know what aromaticity does? It does that stabilization, and it does it better than anything else. If this atom is sp3, and I'm going to posit this as a scenario. If this is sp3, then the system is non-aromatic. And can someone remind me, why do I think it might be sp3? Because it's got 4 electron regions. What if it put that electron pair not in a hybridized orbital, but in a p orbital? If this lone pair sits in a p orbital, it would have smaller bond angles, which means we might start expecting greater electron repulsion. But if the atom is sp2, and this sits in a p orbital, then it's cyclic and fully conjugated, and it's planar. And the pi electrons, 2, 4, 6, the lone pair counts as pi electrons and makes my system aromatic. So why do electrons get put in hybridized orbitals? It's to minimize electron strain. Why would a system choose to be less hybridized? It's to have less strain, to be aromatic. So this structure has 2 options. Go against our intuition and put it in an sp2 hybridized atom, put the lone pair in a p orbital, and get aromaticity out of it. Or follow our old rules and be non-aromatic and lose the stability of being aromatic. It's going to choose this. Now, if you want to see what that p orbital looks like, I've actually got a similar image for you. As you look across this, this top row, here in the middle structure, there's actually an oxygen atom at that point in the ring. You'll notice that there's still 2 carbon-carbon double bonds, but instead of a carbon with a lone pair, it's an oxygen. And you'll notice that that oxygen has a lone pair sitting in a p orbital and a lone pair sitting in a hybridized orbital, an sp2 hybridized. That's the same thing that this electron pair will do. This electron pair will sit in a p orbital, which allows it to be fully conjugated with all of the other p orbitals. I now get a ring. Okay, so the Frost circle, the MO diagram for this this 5-membered ring. I draw my pentagon on a vertex, and I get 5 molecular orbitals. How many pi electrons in my system? 2 from the pi bonds, and so 4 from the pi bonds, and 2 from the lone pair in a p orbital. So 6, 2, 4, 6. Now, because this lone pair is in a p orbital, it's in resonance. So that lone pair is not sitting on any one particular carbon atom. It's delocalized around all of them. So we can abbreviate the cyclopentadienyl anion as an aromatic circle with a negative charge inside. We represent the negative charge and the fact that it's aromatic. Okay, I want to take a similar process, but I want to show something different. This time, let's look at 5-iodo cyclopentadiene. Iodine, as we know, is a good leaving group. So let's try to imagine where this iodine leaves the structure and puts a positive charge on that carbon at the top. Is the structure cyclic? Yes. Is it fully conjugated? Why not? This carbon was sp3, but now, even following our old rules, it has only 3 electron regions, which will repel each other as much as possible, being sp2. So you've got a structure like this too, that very first one on the top row. It shows you what this looks like from that flat perspective so that you can agree that this is also cyclic. Cyclic, planar, and fully conjugated. So is it aromatic, anti-aromatic, or non-aromatic? What a beautiful pentagon. Okay, cyclic, planar, fully conjugated. So we know that it's not non-aromatic. It's either aromatic or it's anti-aromatic. It either gets this electronic stability like its anion version got, or it's going to get some destability for being the cation version. How many pi electrons in the cyclopentadienyl cation? Only 4. Huckel's rules suggest that this will be anti-aromatic. So what is it that's so destabilizing about this structure? Well, first, I'm going to represent this again. What a terrible pentagon. It keeps getting worse. I'm going to represent this again using that circle with a positive charge. Do you remember we said that the circle feels like it might mean 6 electrons? It doesn't. You just believed that because you saw it on benzene. It represents this full conjugation. It does not represent a specific number of electrons. This represents only 4 electrons. 2, 4. Can you see why the anti-aromatic structure is destabilized compared to the aromatic structure? talk in your groups. Take a couple of minutes to see if the frost circle, the MO diagrams, tells you why one is more stable than the other.
So is the N in the 4N, is that just for like kicks and giggles basically?
It's a means to an end.
So it doesn't.
It just helps us, yeah, it helps us take patterns and apply it to structures. Basically, what we know is every time a structure has 4 or 8 electrons, it's anti-aromatic. Every time it has 2, 6, or 10, it's aromatic. And so you can just,
Basically like, oh, if N equals 2, that's 8. If N equals 4, that's 2.
but no, like compounds aren't classified by it. They don't say like, oh, this is a Huckel's N equals 1 compound, you know?
So it's for kicks and giggles.
It is basically for kicks and giggles. It's a helpful generalization. All it does is generalize it for our compounds.
That makes from algebra 6 because there's 2, like 4 pi bonds and then the 2 additional electrons. So that's
Good.
26.
And do you agree that if this atom were sp3, those pi electrons don't become conjugated? The conjugation comes, I erased it, from having a p orbital. Being sp or sp2 hybridized, the conjugation comes from having a p orbital. If this lone pair were put in an sp3 hybridized orbital, then it would not be conjugated. So it only gets the aromatic stability by being sp2 and putting the lone pair in a p orbital.
Would you say that like making it aromatic is even more stable?
That's what it aims for. Yep. It might get some stability by spreading out its electron pairs to repel less with others, but it actually gets more stability by contributing to aromaticity. If it can be aromatic, it will be aromatic. There's actually very few compounds that are anti-aromatic because they avoid being that as much as possible. Okay, anybody willing to tell me what they noticed? Why is the anti-aromatic compound less stable than the aromatic? What do we call unpaired electrons? Radicals. Highly reactive, looking for pairs. Just by looking at this structure, or even by looking at all of its resonance forms, would you have expected that that structure has 2 radicals? Would you have predicted that 2 of these 4 electrons are circling the molecule all the time, and 2 of these electrons sit in different orbitals unpaired? No, why would you? Why would you expect that? Which is another reason why MO theory tells us something that valence bond theory and bond line structures just can never predict. Stabilization by being aromatic, destabilization by being anti-aromatic. Let's go through some more compounds. And this time I want to take another approach. We have this compound. It's the 3rd structure, the one that is placed on its side. It has oxygen in it. This compound is furane, and it is aromatic. What is the hybridization on oxygen? sp3. For context, here's water. Very similar bonding environment, 2 single bonds, 2 lone pairs, and water is sp3. That allows water, that allows the oxygen to minimize electron repulsion. Furane is aromatic. What is the hybridization of oxygen? if the oxygen is sp3, the system is not fully conjugated, and it's not aromatic. This has two options. It can be sp, or it can be sp2 hybridized. Well, sp is not going to be energetically stable. That's too far down. But by being sp2, one of the lone pairs will sit in a hybridized orbital. Remember that sp2 hybridized atoms have 3 orbitals that are sp2 hybridized. One of those orbitals goes over to a sigma bond to carbon. Another one of those orbitals goes to another sigma bond to carbon. And the last of those orbitals holds one of the lone pairs. Well, just beautiful artwork. And by being sp2 hybridized, the oxygen has an unhybridized p orbital where it puts its other lone pair so that it can be involved in the hybridization. Now, in the conjugation. Now that one lone pair is delocalized across the aromatic system. So we describe this as one lone pair being localized and the other lone pair is delocalized. I've put one lone pair in red and I've put one lone pair in green. Can you tell me which color correlates to which description?
Green is localized.
Good. Red is delocalized. Localized, sp2 orbital. sp2 orbitals don't engage in conjugation themselves. Delocalized in a p orbital, and that p orbital actually isn't in a p orbital. It creates a pi molecular orbital. It creates one low energy where everything sits. How many pi electrons in furane? 6 pi electrons. 2 from the double bonds. 2 pi bonds. And 1 lone pair. What do you think? Interesting? Let's apply it to some more structures. And I know I've given you some structures to go through on your own as well, so I think we'll go through these together, but I know you have to copy them down. I'm going to make a small change. This last structure, I'm going to add a nitrogen where there was a carbon. First structure, cyclopropenyl cation. Aromatic, anti-aromatic, or non-aromatic. Assuming that it's cyclic, planar, and fully conjugated. Why? But having it be cyclic, planar, and fully conjugated means it could also be anti-aromatic. It depends on the pi electron count. Being aromatic and anti-aromatic follow the same three rules until the electron count. How many pi electrons? Oh, you can't tell because it's impossible. See, the circle is evil. Sorry, I'm going to redraw this as a line and a positive charge. How many pi electrons? 2. Does that follow 4n plus 2 or 4n? It follows 4n plus 2 when n equals 0. Then the answer is just 2. So for as strange as this little molecule might seem, it's actually quite stable. It's aromatic. Cyclobutadiene.
With the one next to it, right?
To the right.
Is it aromatic?
Anti-aromatic.
Anti? Anti-aromatic. Cyclic. Planar. Fully conjugated with 4n pi electrons, where n equals 1. You agree? Anti-aromatic was 4n pi electrons. This is 4 pi electrons. That does agree with 4n. Anti-aromatic. All right, here's an interesting thing. This compound doesn't like being anti-aromatic. So it will actually stretch its pi bonds far enough apart to become non-aromatic. That same idea we looked at with the bole cyclooctatetraene, that compound will create a bole. It also is avoiding being anti-aromatic. This compound avoids being anti-aromatic by breaking the conjugation between its pi bonds, by elongating its sigma bonds. It does everything it can to avoid being aromatic. Okay, how about down here? This is the cycloheptatrienyl anion.
Anti-aromatic.
How many pi electrons? 8, which follows 4n. So this is anti-aromatic. What change could you do to this structure to get an aromatic compound? Well, this atom actually must be sp2 if we'll count it as anti-aromatic. But what could I do to make it an aromatic ring? Well, it has too many electrons, right? In fact, it has too many electrons. So if I could oxidize 2 electrons out of this ring, well, I know the best 2 to take. There's a lone pair sitting at that negative charge. So if I take those 2 electrons out of the system, I leave the carbon with a positive charge, and now I have 6 pi electrons. Cycloheptatrienyl anion, anti-aromatic. Cycloheptatrienyl cation, aromatic. And actually, this was what I wanted to point out, and I didn't do a good job doing this. I wanted to point out along the top row here, you've got these versions of rings that have 6 pi electrons. These are basically modifications of benzene's electronic structure. They look like benzene a little bit, or they have the same amount of pi electrons as benzene. All right, this last structure is called imidazole. Aromatic? That would mean that this nitrogen has what hybridization? sp2 hybridized. And the lone pair on this nitrogen would be described as localized or delocalized. It would have to be if it's counting towards the pi system. And he's exactly right. This is an aromatic system. This nitrogen is sp2 hybridized with delocalized lone pair. What about the nitrogen at the bottom? How come its lone pair isn't counted towards the system, making the count 8 pi electrons and making it anti-aromatic? What's the hybridization of that nitrogen on the bottom? Also sp2. And I do want to point out this sp2 on the bottom already agrees with our rules for predicting hybridization. There's 3 electron regions: single bond, double bond, pi bond. This nitrogen that we described as sp2 on top broke our rules. We're now following our new aromatic rule. If it makes the ring aromatic, let it be sp2. What about its lone pair? Is it not in a p orbital? To be delocalized, it has to be in a p orbital. And now I'm worried that using red here is bad. I'm going to use green. Okay, let me phrase it this way. On top, the blue atom is sp2 hybridized. So it has 3 sp2 orbitals. It uses one to bond with carbon, another bond to carbon, and the third to bond to hydrogen. It has one unhybridized p orbital, which it uses for its lone pair. This is an sp2 hybridized carbon. It uses one sp2 orbital for a single bond, another for a single bond, and it uses its p orbital for the pi bond. So it only has one orbital left, and that is one of the hybridized orbitals, meaning this lone pair sits just like this lone pair on oxygen from furane. This lone pair is localized. This is a challenge, right? The same atom in the ring twice with the same hybridization, but lone pairs contribute to the aromatic system differently. So one thing that you can try to do is make this like representative. Describe this nitrogen and this nitrogen somehow so that you can tell them apart, or recognize this feature. If this nitrogen is already pi bonded, if it's already using its p orbital, then it can't put its lone pair in a p orbital to conjugate with the pi system. Its p orbital is already busy bonding to carbon. So it can't put anything else in a p orbital. Okay? All right. I do want to take a step back because there were a couple of compounds that were up above that I do want to touch on. Let's take this 6-membered ring that looks like benzene, except it's got a nitrogen in it. And then let's substitute basically the same thing, but with an oxygen. This compound on the left is called pyridine. I actually don't have a name for the structure on the right. I don't know if it is its own compound. Yeah, sure. Pyrrolium. That's what I was going to guess. What do you think about these compounds? Aromatic, anti-aromatic, non-aromatic. First one is aromatic. Second one?
Aromatic. With a radical.
No, no radical. Mm-mm. So all we have essentially done, we've taken out a CH from benzene. And that CH was an sp2-CH bond. Do you guys agree with that? We took out a CH from benzene and we swapped in a nitrogen with a lone pair. Is that lone pair localized or delocalized? It's localized. It's in an sp2 orbital. And you'll recognize that it looks a lot like the nitrogen bonding in our imidazole problem up above. So this is what I was referring to earlier. Nitrogens that are in this double bond already will have localized lone pairs. So you could call this a pyridinyl lone pair. It resembles the lone pair on pyridine, and it's going to be localized. Yeah.
So, like the one up above that you have that has like the green writing.
Yeah.
So, the one nitrogen can't delocalize because it's already connected to a pi bond, right? Because it's p orbital.
Its p orbital is already filled, so this lone pair can't go in the p orbital.
But then the one above, it's not double bonded to BP.
That's right.
It can be.
So it can put its lone pair in the p orbital. And that's what the p orbital does. When you place a lone pair in that p orbital, it creates a conjugated system. If the lone pair can't be in a p orbital, for instance, because the p orbital is already filled, then the lone pair has to go in a hybridized orbital, and it's not conjugated. So to be conjugated is delocalized, to be non-conjugated is localized, and it comes down to the molecular orbitals.
So if there was no hydrogen on that one,
Mm-hmm.
would be anti-aromatic?
On this one.
This nitrogen, yeah.
Well, there's a lot that would have to happen. Do you mean like if this was empty and had no lone pair?
If there was two lone pairs, like if you got rid of the hydrogen.
So if the hydrogen was gone and there was a second lone pair,
Yes.
then first of all, the nitrogen is negatively charged
Yeah.
because it has two bonds, two lone pairs. The second lone pair goes into an sp2 orbital. It would actually resemble exactly the oxygen layout from furane.
So it would still be aromatic.
It still would be aromatic. Let's look at this example, the pyrrolium compound. Because we looked at oxygen when it had two lone pairs. We said one of oxygen's lone pairs is delocalized, one is localized. What about in this case? Is the lone pair that remains on oxygen? You know why there's only one lone pair on this oxygen? It has it's got 3 bonds. So 3 bonds, 1 lone pair. Is this localized or delocalized? Do you want to explain why? Why do you think it's delocalized? To be delocalized, it would need to be conjugated. To be delocalized, it would need to be in a p orbital. So you want this lone pair to be in a p orbital. But the oxygen is already using a pi bond. So to have 2 p orbitals, it would have to be sp hybridized. And this oxygen won't. It won't become sp hybridized.
Well, the oxygen doesn't have a charge, it's just neutral, and it has a lone pair and an extra electron. What does the extra electron do?
Well, first of all, to put another electron here and get rid of the positive would break its octet. Yeah. Yep.
Would it be localized?
This lone pair is localized. This carbon, or this oxygen is also sp2, and its lone pair is in that sp2 orbital. Remember what we said about nitrogen earlier? It's already using its p orbital, meaning its lone pair cannot be delocalized. Already using its p orbital, its lone pair must be localized. Have you guys formatted a question that I can go through?
That's fine. You can explain it better than I can.
I'll do my best.
I mean, in my mind, I'm like, okay, so if it's negative, it's pretty much like not always going to be aromatic, but like.
No, the charges have nothing to do with it.
Okay.
I know. Here is a negatively charged aromatic compound. Here is a positively charged aromatic compound. Here's another positively charged aromatic. Here are the things I want you to be able to do. Recognize hybridization when it goes against our expectation. We expected this oxygen to be sp3, but we found it was actually sp2 in order to be involved in aromaticity. So, recognizing new hybridization rules. That's one of the things I want you to be able to do. The other thing I want you to be able to do is look at a lone pair and decide, is it localized or delocalized? Is it in a p orbital, delocalized across the entire aromatic ring? Or is it in a hybridized orbital and it's localized to that atom? It's not in a p orbital, it's not contributing to aromaticity. Those are the two primary things I want you to be able to do here. I have more practice problems for you, and I want you guys to finish those. So on the bottom right of this worksheet, we've got all of these different compounds. How many is that? 3, 5, 7 compounds. I want you to decide whether they are aromatic, anti-aromatic, or non-aromatic. But before I give those to you, there's just two last things I want to say about this. First of all, to be aromatic means to have aromatic character. The entire molecule does not need to be aromatic. There can be portions of the molecule that are not cyclic, not part of a ring, not conjugated. There can be parts of a molecule that don't have anything to do with aromaticity. But if part of the molecule has aromaticity, then it has aromatic character and it's an aromatic compound. Does that make sense? For instance, the compound phenylalanine. I think I drew it wrong. Phenylalanine has aromatic character. It is an aromatic compound because it has the aromatic ring. Most of the compound does not have aromatic character, but it has a benzene ring that does have aromatic character, right? We can say the same thing about anti-aromatic character. Polycyclic rings contribute towards aromaticity all at once. If these rings are fused together, all of the pi electrons count. For instance, we know that benzene is aromatic, and we know that cyclobutadiene is anti-aromatic. So this structure may strike some of you as being aromatic on one side, anti-aromatic on the other. But because this is bicyclic, we count all of those pi electrons together. So I count 2, 4, 6, 8 pi electrons. anti-aromatic system. And I hate to say it, but this is not always true. There are actually some arenes, just hydrocarbons, that break Huckel's rule, so it doesn't really hold up all the time. I'm not going to give you those problems. We're going to look at the problems where this is the case. Okay, last thing I want to mention here. That conjugation must be completely within the ring. And I have some cool examples for you guys. So this compound, I always forget its name. Quinone. Great. Convinced myself. This compound is quinone. And as you go through to try and decide whether it is aromatic, anti-aromatic, or non-aromatic, you might convince yourself that every atom is sp2 hybridized. So it's fully conjugated. But then as you start to try and consider pi electrons, there's only 4 pi electrons within the ring, and then there's another 4 that are technically outside of the ring. So do I count just 4 pi electrons? Do I count 8? Either way, I'd expect this to be an anti-aromatic compound, and it's not. It's quite stable. It's not aromatic stable, but it's not unexpectedly destabilized. When we say that atoms must be fully conjugated, we mean that their pi electrons, their pi bonds, must be completely within the ring. Since these pi bonds break out of the ring, we would say that this structure is not fully conjugated. Those 2 atoms where the pi bonds escape the ring, they're no longer conjugated with the rest of the ring. Okay, we have biologists in here? Yeah, good. Your DNA is made up of these little nucleotides. And a lot of those nucleotides are quite stable compounds. And yet you might not describe them as aromatic. So we've got adenine here, aromatic. It's actually got an aromatic ring on the right and a second aromatic ring on the left. 2, 4, 6, 8, 10 pi electrons. Guanine, also aromatic. But thymine, cytosine, uracil, technically not aromatic because we've got those carbonyls that break the conjugation in our ring. But there is a resonance form that can be drawn for these compounds that actually creates aromaticity inside the structure. If these nitrogens share their lone pairs and break the pi bonds to the carbonyls, we get a resonance form that does technically increase formal charge. But it creates that 6-membered ring. Every atom is conjugated, 6 pi electrons. So this is a resonance form that creates aromaticity. I forgot my positive charges on the nitrogen. It creates aromaticity by creating 4 charges. So how likely does this form contribute to the resonance of the molecule? It's hard to say. It maximizes charge, but it maximizes aromaticity at the same time. So there's some trade-off between its stability. Not to mention, negative charge on oxygens means better hydrogen bonding between counterparts of the DNA. Stronger positive on the nitrogen also means stronger hydrogen bonding between those components. So this resonance form may actually strengthen aromaticity in the ring and improve hydrogen bonding between different strands of the DNA. Cool, thanks for listening to that. Why don't we take a break? 5 minutes, we'll come back at quarter after, and we'll solve what's left of these problems before we jump into what's new. Pop quiz?
Sure.
What's the hybridization of this nitrogen?
SP3.
What's the hybridization of the same nitrogen in the next structure?
SP2.
Oh. Different hybridizations? What's different about these structures? Like, how do they relate to each other?
They both have a nitrogen. They're both cyclic.
What does this arrow mean the relationship is between them?
It's the same structure, just means the electrons can move to a different place.
They are resonance forms,
And they're resonance.
which means neither one actually exists.
It means what exists is that the electrons share both of
That's right.
the spaces and time.
So how can the electrons be sp3 and sp2 at the same time?
Because they're at both places at once. Because they exist.
But sp3 orbitals, the orbitals that they would be held in,
It's the same thing.
but the sp3 orbitals aren't the same as the p and the sp2 orbitals. So if it's sp2 at one point, then it must be sp2 all the time. And if it can be involved in resonance, then it must be sp2. And so even here, where we still expect it to be sp3 because we have those rules, we have expectations, but if it can be involved in resonance, and they like to be involved in resonance, then they have to be sp2. Okay, did you go through the rest of the compounds?
Isn't that four? Pi electrons though?
2, 4, 6. You agree?
Yeah.
So you mentioned that one sp2, so the lone pair should be the p orbital, right?
Yes.
Oh, frick, I didn't write any of that.
Okay, solve these problems. See if they are aromatic, non-aromatic, or anti-aromatic.
Can I ask you, like, probably, like, a Gen Chem 1 basic question?
You sure can try.
Okay. So, because I always, like, mix it up. So when there's a negative charge, it means that it has the electrons and it hasn't made a bond. And then when there's a positive charge, it means it got its electrons, like, stripped away, right?
Well, are you talking about just like in general an atom?
Yeah, like, just in general, because it's, like, the two, like, the anti-aromatic and the aromatic, one of them, it still has its...
Yeah. So if it's carbon, carbon with a negative charge holds a lone pair. Carbon with a positive charge has an empty orbital.
Oh, yeah. I would think, yeah, just, like, meaning in carbons, but then, so, like, when the oxygen has a positive charge, then that means it's... Or if something has a positive charge, does it mean it's missing a pair of electrons?
Not always.
Frick.
Yes. Frick indeed. So the oxygen has a full octet. In fact, one of my OChem 1 students had this problem on her first unit test, and it was asking to go through and show formal charges. So they had this structure. It actually had all lone pairs, all hydrogens shown. and it said, where is the formal charge correct? And I had 4 different structures, so
Oh, you did that on ours too.
it was the same unit test. Positive on O, negative on O, positive on N, negative on N. Her reasoning was to put negative on O. And she said, without the negative, it's going to break its octet. If oxygen has a positive, then it must be breaking an octet. And that's because I nailed into them that carbon with a positive is missing an octet. So she transferred that and said, then oxygen can't have a positive charge. Oxygen can't have a missing octet. It's 2 electronegative. So it must be negative because something seems wrong about that oxygen. It must be negative. But we can go through the formal charge equation. Formal charge equals valence electrons, 6, minus dots plus lines, 1, 2, 3, 4, 5. 6 minus 5 is plus 1. So the odd thing, carbon is the odd one out.
Okay.
When carbon holds a positive charge, it's got an empty orbital that things can come to. Oxygen with a positive charge, neutral. Nitrogen with stable, octet filled, positive charge, neutral. Nitrogen with a positive charge, full octet.
Yeah.
It just has to do with, is it sharing more electrons than it wants to?
Okay.
Does it have more electrons to itself than it wants to?
Okay.
And wants to is a general term.
Yeah.
Carbon likes to have 4 bonds. Nitrogen, 3. Oxygen, 2. Halogens, 1. So
Then when it's, oh yeah, so then like if nitrogen's sharing.
it's sharing more electrons than it wants to.
Okay, yeah.
Exactly.
Okay.
It has
But, like,
less electrons
I think
to
it's,
its
like,
disposal.
carbons that, like, throws me off because I'm like, there's no lone pairs there.
You're right. And that's why carbon is the backbone of life, because what it can do, most other atoms can't do.
Thank you.
You're welcome. Yes, see if you can find your
Like the.
see if you can label them as aromatic, anti-aromatic, or non-aromatic.
Useless. That's how I felt about like cells in biology. They're like, oh yeah, they do this. I'm like, did they tell you? Like, how do we know that they did this? Did they tell you? Did these OChem compounds tell you?
The NMR told me.
Wait,
Yeah.
why are we so serious?
Okay, we're kind of getting it kind of. So this one, this is conjugated.
Yes.
Conjugated. So
Yes.
yes.
But it's
Then-
polycyclic, so you need to count
All the electrons.
all of the electrons in both rings.
For it to be conjugated.
Including the lone pairs.
Any lone pairs that are
They're localized or
no, you don't count localized lone pairs toward the aromatic pi count.
So you
Only the
just count
delocalized.
These lone pairs.
That's right. Yep.
So is there 10?
That's right.
Okay.
Good.
Thank you.
Good. You guys trying at this? Label them as aromatic, anti-aromatic, non-aromatic. Good.
Yeah, I mean, obviously.
I hope so.
I mean, okay, if it's not, then I mean, it is what it is.
Any others?
I just kind of really started.
Okay.
Wait, so, okay, I have a question. So, every time we see a double bond, right?
Yeah.
That's 1 pi electron?
No,
No, 2.
2 pi
Okay,
electrons.
2 because, yeah.
Because
right.
each line represents 2
2
electrons.
pi and then 2 sigma, we won't care about the pi's. Because
That's right.
Okay.
That's right.
Okay. We're not dealing with triple bonds yet, right?
No, and we probably won't.
Okay. But if there was a scenario where that was the case, it'd be 4, 5
There would be 4 pi electrons,
per bond.
but one of those pi bonds would be perpendicular. So only one of those pi bonds would actually conjugate with the rest of a system. The other pi bond wouldn't be at the right angle.
Okay. Oh, is that why it has to be planar bond?
Yeah.
So it's just this one now, aromatic, and all the others?
No.
This one now? Okay. Oh, this part.
Not just that spot, Yoon.
only this one is just not kind of fully
Not just that spot though.
Not just
Where
that.
else? Yes, and
this one.
so there's actually 3 carbons there.
Okay, so just these two. is
That's
gone
it.
right out.
Yep. How'd you do, Max?
Oh, I mean, I don't know how I did, but that's the best I got so far.
Great work. Did you notice how many anti-aromatics there were on there?
Oh, there was 0, right?
Right, because they're just not very common.
Yeah, I know.
Yes. Yes.
So for this, how do we know if like what is out here matters? So like
It won't.
it doesn't matter.
It won't matter. Anything that's connected off of the ring won't matter at all.
Oh. Oh, but the oxygens mattered because they were connected.
Because they were pi bonds. Yeah. So they screwed up what we consider conjugation.
Oh.
Yep.
But like that doesn't matter because it's not in the ring, right?
Exactly. Could have been a hydrogen. All right. So for you guys in the back, I want you to take this 5-membered ring that you're given on the structure. Sorry, this 5 and 6-membered ring. And I want you to draw a resonance form that highlights aromaticity in both rings. So I want you to move the pi electrons however you need to create aromatic character in both of those rings.
I had a question about like,
Mhm.
does it count as one? So is it 1, 2, or just 1? Because it's the nitrogen is being used as on the pi one. So does it count as well, or is it because it's not it's not carbon yet?
So these pi electrons,
Yeah. Is it 1, 2, or will it just be 1?
we'll never count just one pi electron from a pi bond. So this pi bond has 2 pi electrons, both get to count. Yep. So what did you find about, you found this one to be anti-aromatic because there were 8. Can you tell me where those 8 were?
It was 1, 2, 3, 4, 5, 6, 7, 8.
Good. And the way that I would count them is actually on the line, 2, 4, 6, 8, rather than like atom by atom. Count the bond. Okay, but you didn't count this atom, and if this atom is not conjugated, then I don't have to count the whole ring. And if this atom is conjugated, then it must be bringing some electrons. And in fact, this nitrogen looks a lot like the nitrogens we saw earlier, where the nitrogens create an aromatic ring if they are sp2 hybridized. And their lone pair is delocalized. So now we have 2, 4, 6, 8, 10. The lone pair from the nitrogen contributes 10 pi electrons, aromatic.
1 minute, and it's like the little like 8-bit people.
The outside ones don't count, right?
You guys are starting up here. Oh, are you doing that problem? Trying to draw a resonance form? Okay. But I do want you to think about these compounds because that's more of what you're going to deal with. Assign them as aromatic, anti-aromatic, non-aromatic.
Okay, I'm kind of understanding, but I'm just getting a little confused. I know that one of these is going to be delocalized and the other is going to be localized.
Good.
But like, then I go here
Mhm.
as this methyl group.
Right.
So is this going to be delocalized, or it will be localized?
It's a good question. If it's localized, it means it's in a hybridized orbital. If it's localized, it doesn't count towards the pi system.
Yeah.
It's not in a p orbital. It's not conjugated. So if this is a localized lone pair, then the ring is non-aromatic because it's not fully conjugated.
Yes, okay.
If it is delocalized, then I get 2, 4, 6 pi electrons. Aromatic.
So we.
So it would favor the aromatic.
It favors aromaticity.
Okay.
It favors delocalizing its electrons.
Okay, I see. So are none of these anti-aromatic?
None of them are anti.
Okay.
Yep.
Looks like that family favor. Thank you.
Good question.
Yeah.
Would this be a resonance structure, or did I just literally draw the same thing?
Yep, you just do the same thing.
Shit.
Yeah, there's no pi bonds that moved.
Okay, so we have to move the pi.
That's what resonance is. Yep. Resonance is the movement of the pi electrons.
break, get split, make it.
Mm-hmm. Does that make the rings aromatic?
Yeah, this part I know is kind of like aromatic.
Mm-hmm.
Yeah.
Oh, I erased it. But we did it over there. And this one we did over here.
Yeah.
So they count.
So it's stable like that?
Mm-hmm.
Oh, my brain. Wait,
Yeah.
All I did was just move the pi electron to make a positive, I don't know.
Well, you made a positive without making a negative, which is concerning because you can't create charge from nowhere. The negative would actually be on that carbon because you have 5 bonds going to it.
Oh, yeah.
So you'd have a negative, but you would have broken the octet. All right, let's go through some of them. Structure number 1, adenine. Aromatic, anti-aromatic, or non-aromatic? What say you? Why? Sorry, did someone say the water test? 10?
What are we looking at?
Oh, we're looking at adenine. 10 pi electrons. How many electrons on the nitrogens are delocalized? How many? 1 lone pair is delocalized. This nitrogen has a delocalized lone pair. 2, 4, 6, 8, 10. All of the other nitrogens are actively pi bonded. So all of the other lone pairs are all localized.
How many bonds are there, or pi things, what are they?
The pi electrons?
Yeah.
Well, I count that 1 delocalized lone pair.
You count the delocalized ones?
That's the point. Yeah.
I thought you weren't supposed to count them.
No, they count towards aromaticity. That's why they're delocalized. They're not at the nitrogen. It looks like they're at the nitrogen, but I bet it also looked like this didn't have any radicals. And you remember how many radicals this had? 2. It looks like those are nitrogen's electrons, don't they? They're not. Those electrons aren't on nitrogen. Those electrons are delocalized to the ring. My next structure, tryptophan. Tryptophan is an amino acid. Aromatic, huh? Makes you sleepy on Thanksgiving. Tryptophan's bicyclic structure basically replaces 3 of the nitrogens. It just replaces the 3 nitrogens with localized lone pairs that weren't contributing to aromaticity anyways. It replaces them with CHs. So the only difference between adenine and tryptophan is the position of those 3 nitrogens. What about proline? Somebody said anti. Can I hear from you? There's 2 pi electrons. There's 3 sp3 carbons in the ring. Is that what you're saying? There's 4. This ring is non-conjugated. It's not conjugated at all. There's no pi bonds. So this nitrogen is actually sp3, and this is a non-aromatic system. It doesn't follow any of Huckel's 3 rules, cyclic, planar, or fully conjugated. What about pyrrolysine, pyrrolysine? Also non-aromatic. That 5-membered ring, very similarly, I'm just going to draw R here, is not fully conjugated. There's actually 3 different positions on this ring that are all sp3 hybridized. Histidine, aromatic, 6 pi electrons. The lone pair on the nitrogen in histidine, delocalized, good. Oxadiazole, aromatic. How many of oxygen's lone pairs are delocalized? 1 is delocalized. How many of nitrogens? None. You guys are picking up, huh? You getting it now? 1 localized. 1 delocalized. Okay, what about imidazole? Aromatic. For the same reason as, well, actually, this is wrong. This is methyl imidazole that's on your paper. So I'm not sure why I wrote it down as imidazole. The one we did earlier was imidazole. This is methyl imidazole. Okay, is it getting easier to imidazole? Yes. Histidine is aromatic. What other ones do you have questions on?
If at least one of them is delocalized, then it's aromatic?
Not necessarily. It could still be anti-aromatic.
No, if one of the lone pairs, if it has 2 sets of lone pairs, if one of them is localized.
Yeah, so this happens a lot with oxygen. When oxygen has 2 lone pairs, 1 is delocalized.
That makes it aromatic.
Yep, contributes to the aromaticity. 2, 4, 6 pi electrons. Okay, for this structure up here, where we can draw a resonance form that makes both rings aromatic, we should remember that the 5-membered ring wants to be like benzene and have 6 pi electrons. Currently only has 4. So to get 6 pi electrons, the pi bond in the middle needs to move back towards that 5-membered ring. That's going to create a positive charge on the 3-membered ring. And we saw that also follows Huckel's rules. So we can draw this as a circle with a negative charge and a circle with a positive charge, because the circles don't mean anything except for what you want it to mean. And in this case, we mean 6 pi electrons but negatively charged, 2 pi electrons and positively charged. All right, if you thought I was going to let you out early, you're wrong. Just keep trucking. Sorry. Is she coming back? Thank you. I saw a really interesting mechanism recently, and it was talking about methylation. Do you guys know what methylation is in DNA? It's a way that cancer is formed. Your DNA gets methylated. And it involves some of these resonance forms and aromatic rings. So here is cytosine, and you can see where cytosine gets methylated. Part of the way that this happens is by these nitrogens donating electrons to this carbon position so that this carbon is electron rich and then can go out and be a nucleophile to a reaction. And this is actually what we're going to look at in our next section. So we're moving out of aromaticity and we're moving into reactions on aromatic rings. I want you guys to recognize the difference between the reactions we did on Tuesday and what I mean by this. This is reactions on aromatic rings. What did we do on Tuesday? Adjacent to aromatic rings. Reactions on benzylic positions. So now we're going to do reactions right on aromatic rings. We're going to go through substitution on aromatic rings. The general format of substitution here. Take an aromatic ring and run an addition reaction on it. and create this sigma complex intermediate. All right, this sigma complex is about as ugly as it can get. I'm going to say let's start with R1 attached to our ring. We're going to get something else on that ring, R2, and adjacent to that position, we're going to have a charge. Okay, represent that charge as positive or negative. We're going to see reactions that create both types, a positive intermediate, a negative intermediate. This is followed by an elimination reaction. And voila, R1 is substituted for R2. So to do substitution on an aromatic ring, we do addition followed by elimination. You can see how those two steps cancel each other out. Add something, which means consume a pi bond. Eliminate something, which means create a pi bond. So all in all, I'm just substituting one group for another. If you watch my past semesters on this section, you'll notice that I'm going to teach it in a different order than normal. I'm going to start with the reaction that is far more familiar with all of us, that involves what I think you all will see as easy resonance forms. And then we're going to come back to look at the more complicated, but by far the more useful of the two types of substitutions. And hopefully we'll have some developed resonance skills with it. So the first class of aromatic substitution that I want to look at is nucleophilic aromatic substitution. This is sometimes called NAS, as you can see, nucleophilic aromatic substitution. But it's also sometimes called SNAR. That's not SN1, that's not SN2, that's SN aromatic. You substitute an aromatic ring with a nucleophile. For whatever reason, this and the other type of aromatic substitution reaction that we'll name, their names basically describe themselves backwards. Nucleophilic aromatic substitution, substitute the aromatic ring with a nucleophile. Okay, there's two roles in a substitution reaction. There's a nucleophile and an electrophile. If we are substituting the aromatic ring as a nucleophile with a nucleophile, then how does the aromatic ring play a role in this? Right. The aromatic ring is our electrophile. So I want you to think about that. In these reactions, we want the ring to have some sort of positive character that nucleophiles will be attracted to. The thing we'll be substituting are aryl halides. Back in OChem 1, when we learned about SN1 and SN2, we said that those substitutions with nucleophiles could only be done on sp3 carbons. We said vanillic halides were out and aryl halides are out. Well, now we have a way to substitute aryl halides, unique from SN1 and SN2. In order to do this, though, we need strong nucleophiles. So the nucleophiles that we'll use predominantly are things like hydroxides and alkoxides. Those were strong nucleophiles back when we did reactions with SN1 and SN2. They're still strong nucleophiles. We'll see similar things with nitrogen groups. Nitrogens can be a little bit more diverse. We can have amide, NH2-, or a primary amide or a secondary amide. So we can diversify what groups are coming on with that nitrogen. The ones that we won't see as often, these are our most common. We can run this with nitriles, and we can run this with carbon groups. Carbon groups that have a negative charge, like the acetylide ion, the alkyne conjugate base. Those are good nucleophiles. At the top of your worksheet, I've got a generic reaction. Everybody got one, right? A generic mechanism that walks us through what needs to happen for NAS. So I want you guys to fill this out with me and fill in what happens with the pi bonds as we go. You'll notice the pi bonds aren't shown in the middle structures. Thank you. Okay, in this generic example, I just show that the intermediates have nucleophile on them. If you want to, you could swap that out by picking an actual nucleophile, but we're just going to show it like this for now. Nucleophile attacks the partial positive carbon that's bonded to the halogen and breaks one of the pi bonds into the ring. This starts our sigma complex. Remember, we said the sigma complex will have this R1, R2, and adjacent to it will be a positive or a negative charge. Well, now we know that NAS holds a negative charge in it. Of course it does. The nucleophile has donated electrons to our ring. After this, we don't see a reaction arrow. What's the next arrow that we see? Resonance arrow. Because this sigma complex is in resonance. I have a negative charge, so that negative charge will become a pi bond to the adjacent carbon, and it will break the adjacent carbon's pi bond off into a new lone pair. A lone pair in, a lone pair out. My negative charge is in a new position, but my negative charge is still conjugated. So lone pair moves in, lone pair moves out, and I get a third resonance form. For the elimination step, a few things to consider. 1, I started with aromaticity in my structure. That's a desirable thing from an energetic standpoint. Does my sigma complex have aromaticity? Why? It's not fully conjugated. This position of my sigma complex is not fully conjugated. It's sp3 hybridized. Good or bad? Okay, that's anthropomorphizing. We're telling it how we feel about it. Bad. From an energetic standpoint, it's bad. I've lost my aromatic stability. So a desirable thing from an energetic standpoint, reform aromaticity. That means I need to get another pi bond right here. And to get a pi bond here, I'm going to have to kick off one of these two groups. Okay, we also haven't done substitution yet. I started with R1. I need to get rid of R1. In this case, we're saying R1 is bromine. So my lone pair goes in, my my CBr bond breaks. I'm going to go back to using my other color because that is the end of my resonance forms. And this next step is actually not showing resonance, it's showing the formation of the final product. Now, you guys see that on your structure or on your worksheet, I left this blank. I didn't put the aromaticity back in. Well, that gives you a choice. You can put in the 3 alternating bonds of benzene, or you can draw it as a circle, because we're agreeing that if the electrons are not necessary for something we're showing, then this is what we can do. Okay, I think with the time remaining, what I'd like to see you do is take this generic layout and copy it for the next reaction where you see chlorobenzene react with methoxide. This time, we show a real nucleophile, we show the resonance forms, we show the formation of the final product. Can you show me the nucleophilic attack?
Yeah.
Good, Yoon. Good job, Jackie. It's okay. This stuff takes practice. Good job, Peyton. Struggling? I know you weren't there for most of the fall, but this worksheet,
I know.
the
it's really
version,
useful, it's
the version I did of this in the fall was terrible. It was terrible.
Because I'm looking at this, I'm like, why was I using this?
Because I didn't make that. The first worksheet I made for your class in the fall was on this topic, but it was like the worksheet was just way too convoluted.
Yeah, this is actually fun.
Great. Good. One thing I like what you guys are doing is starting with the templates. You know how many steps you're trying to show, and then coming back in and filling in the arrows. That works really well. Perfect. Well done. Our time is almost up. Looks great. So when you are ready to go, you're good to go. If you want me to check off your work, I'll check it off before you head out. On Tuesday, we'll wrap up this worksheet and we'll look at our other type of substitution as well. And next Thursday, we'll do multi-step synthesis with all these reactions.
Exciting.
Yay. Perfect. Well done.
Thank you, this. It looks really sloppy, but.
We're missing the bond,
All right.
like
yeah.
this, where the pi bond breaks
You
open.
also show the mechanism too?
Yep.
Okay.
Yeah, that wasn't very clear, but I am looking for the mechanism. Good. Good. Yes. And then just add in those arrows when you get back to it. Great. Bye, Sarah. Have a good weekend. Good. Great. Yes. Yes, yes, yes. Almost.
Oh, and then this one pops up.
Yes. Great job. Great, 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 great. Good job.
I'm just.
Oh yeah, I don't know if you saw my comment, but the part B, the last step didn't have a structure. It was just blank.
Oh no.
So I put it on the picture. I said, no picture shown.
Okay, then I might send you something else, okay?
Is this meant to go into that?
Oops, sorry. Yes.
Okay, I wasn't sure.
Yes, it does. So, perfect, perfect, perfect. But here, we're missing the arrows. And it'll look the same as here, but I can see you didn't do it here either.
No, you're good.
Negative charge reforms the aromatic ring and kicks off the Br. Take care, Yoon.
But then how are you getting?
This structure was meant to be a chlorine, not a
Yeah,
bromine.
I don't know. But
Mm-hmm.
how would you get to OME? What is
OME is OCH3.
methyl?
Yeah,
Okay. I was like,
that's a good question.
okay.
And I actually didn't do that to trick you. I guess I didn't notice
I
that.
didn't think it was like to trick me or anything. I was just like,
Take care, Belen.
want to make sure I know what I'm doing. Okay.
Mm-hmm.
Okay. I was like, so I don't think that connects. I don't understand where you get a different thing from.
So, and actually the I didn't even think about this. The issue with that structure, you kept both groups on,
But one of them has to.
and then you said there was a double bond. So that'd be 5 bonds.
Yeah.
Bye, Katie. Bye, Jackie.
Okay.
Okay, I want to see the arrows. Good.
So I have to like.
It's okay.
Printing.
Do what you got to do.
So is it? It's breaking.
Chlorine takes the electrons. Yep. Great work.
Thank you.
You're welcome, Lily. Have a good weekend.
Okay, wait, can I ask one more question?
Yes.
About the aromatic,
If the compound's aromatic or not.
Yeah, yeah.